Let's take a look at section 3.2, page 13 of your notes on transition metal and their ions in redox systems. In your syllabus, you have to learn two objectives over here. You have to learn to describe and explain the use of these three pairs as examples of redox systems. Okay, and they include iron 3 plus / iron 2 plus, manganate / Mn2 plus, dichromate / chromium 3 plus. These are all redox systems. You also have to learn to predict the likelihood of redox reactions, whether it is likely to occur or not, using E0 values. This is what you have already learned in Electrochem Part 1, so this is a recap here. We are going to look at oxo and ions of transition elements. So what is meant by oxo and ion of transition element? Let me give you an example. Manganese is an oxo and ion of the transition element manganese. So as the name suggests, oxo anion means that overall there's a negative charge, therefore it's an anion. And this oxo anion contains the transition element manganese that is bonded to oxygen. Okay, so this is an oxo anion, and I just want to point to you that this thing, okay, Mn7 plus, simply does not exist. Please do not give me this. Okay, you know that it is energetically too unfavorable to lose or gain more than 3 electrons in general. So therefore, we are not going to get Mn7 plus. Okay, so manganese in the plus 7 oxidation state will be an oxo anion. So this oxo anion of transition element, they tend to have higher oxidation states. For example, you can see that in MnO4 minus, its oxidation state of manganese is actually plus 7, which is very high. Okay, so it makes sense because oxygen is more electronegative than manganese. So oxygen will pull electrons towards itself more. Oxygen get a minus 2 oxidation state, and manganese plus 7. 7 minus 8 is minus 1 overall charge. Okay, so over here we see that the transition element in the oxo anion has a very high oxidation state, and therefore they can be easily reduced. And if a species is easily reduced, it is a good oxidizing agent. Hence, manganate is a very powerful oxidizing agent, as you are very familiar with, because manganate is easily reduced to Mn2 plus. So nothing very new to you. Manganate is easily reduced to Mn2 plus. And this can be seen by the very positive E0 reduction. It is a highly positive E0 reduction over here. Can you see that? Highly positive. It's positive 1.52 volts, signifying that manganate is easily reduced. Correct? A very positive E0 reduction tells us that the species is easily reduced. So if you were to compare manganate in the acidic medium and dichromate in the acidic medium, you will find that this is actually more positive. Okay, this is a more positive value. Okay, the reduction of manganate to Mn2 plus has a more positive E0 reduction. This tells us that manganate is more easily reduced than dichromate. Therefore, manganate is a more powerful oxidizing agent. Okay. So therefore, this is nothing new. You have learned this in Electrochem Part 1. The larger the E0 reduction, the more readily the oxo anion gets reduced. Okay, so this section tells us that oxo anions, the transition elements, they tend to be good oxidizing agents because of their very positive E0 reduction. What about the transition metal elements themselves? They tend to be reducing agents. Why? Because a reducing agent is easily oxidized. And indeed, the transition metal elements themselves are easily oxidized. As you can see, if I'm talking about manganese metal, the manganese metal is easily oxidized to Mn2 plus, as indicated by the positive E0 oxidation values. Please take note that if you're talking about oxidation, you should have a subscript OX here. Okay. So in general, we say that the more positive the E0 oxidation, the more likely it is the metal is oxidized. The more likely we can oxidize the transition metal, and the more readily the transition metal gets oxidized, then it will be a better reducing agent. Is it correct? Because you understand that a good reducing agent must be easily oxidized. So therefore, if I want the transition metal to be a good reducing agent, it surely has to be easily oxidized. If you compare manganese and vanadium, who is a better reducing agent? It has to be the one that has a more positive E0 oxidation. The more positive the E0 oxidation value is, the more easily vanadium is oxidized, and therefore vanadium is a better reducing agent than manganese. Slightly, because the difference is not that great in the E0 oxidation values. Now, the last bullet point is talking about the reducing ability of the metals. It drops across the first row of transition elements. Why? It becomes a poorer and poorer reducing agent as we go across the first row. The reason is simply because if I want it to be a good reducing agent, the transition metal, it must be easily oxidized, correct? And to be easily oxidized, it must lose electrons. Okay, in order for the metal to be oxidized, it must lose electrons. And to lose electrons, okay, it is actually getting harder and harder to lose electrons as we go across the first row because of increasing nuclear charge. Okay, so for example, the copper nuclear charge is higher than the vanadium copper nuclear charge, and therefore it is harder to remove the electrons from copper to oxidize copper. Okay, therefore it is hard, since copper is harder to be oxidized because it's harder to remove the electrons, right, from the stronger attraction of the nucleus, the more positively charged nucleus. Therefore, copper is less easily oxidized, and it is a poorer reducing agent than vanadium, for example. Okay. Now let's take a look at this example of oxidation of Fe2 plus to Fe3 plus by acidified manganate. If you take a look at this, you will realize that manganate, being a good oxidizing agent, is easily reduced. Okay, and so this is what happens here. Manganate is being reduced to Mn2 plus in acidic medium, and Fe2 plus can become oxidized. Okay, I cannot write very well on this. Okay, let me try. Fe2 plus is oxidized to Fe3 plus. And the E0 cell is E0 reduction plus E0 oxidation. E0 reduction is this value, positive 1.52. For the oxidation process, because I'm going the reverse direction, E0 oxidation is negative. I need to flip the sign because I'm going backward. So it's negative 0.77. And the E0 cell is a positive value. Okay, I want to stress the importance of this positive sign because the positive value of E0 cell is important and must be indicated because it's something like a vector. So do not just give E0 cell is equal to 0.75 volts, you will be penalized. And because E0 cell is positive, reaction is energetically feasible and a redox reaction can take place successfully. So you know that in the presence of a strong oxidizing agent like manganate, Fe2 plus is oxidized to Fe3 plus. Let's watch the next video that illustrates this. Now we are going to look at this video over here that shows the addition of manganate to water first. You get a purple solution. Please watch what happens when we add this purple manganate solution to Fe2 plus aqueous. Iron 2 aqueous is pale green in color. So when we add drops of manganate inside, at first the purple manganate is decolorized because a successful redox reaction takes place between the purple manganate and the Fe2 plus aqueous, and thereby reducing the manganate from purple manganate to Mn2+. Mn2+ is almost colorless. And you will see that the solution Fe2+ aqueous was green at first, and as more and more manganese is added, actually what happens is that Fe2+ is oxidized to Fe3+ aqueous, and the color is actually yellow. Fe3+ aqueous is yellow in color. Okay, I hope that you can see the color intensity actually increases. It's actually a yellow solution.